So actually, I'm sort of with Alpine High Performance Products. Rather, I'm with AE Building Systems, and we're a manufacturer's rep for Alpine. We're also a manufacturer's rep for a company called Advantage Architectural Woodwork. They're out of Colby, Kansas, and they're making European windows in Kansas. We distribute other products, for example, ERVs from Build Equinox out of Illinois. And we distribute Sega tapes that are out of Switzerland. Sega's got a presence in the US, and we've been working with all these companies to some degree since 2011. I officially started AE Building Systems in 2011. And to give you some background on me, I'm actually a recovering computer science guy. My undergraduate degree was computer science. I wrote code for about 4 years and nearly went out of my mind. And went back to school and got a degree in marketing and entrepreneurship. I ended up doing marketing and technology and then sales and technology, and then we had kids. And I always had an interest in the built world, the building environment. So when we had kids, I realized that I needed to be home for dinner. And I was traveling a ton, at least 30%, and should have been more like 50%. So I went back to this old concept of the building world and always had an interest in passive SOAR design. In researching how I might insert myself into that industry, I found Passive House. And it made so much more sense even than passive SOAR design. I'll give more information on Passive House, but I started AE Building Systems with the concept of being a sales rep that can actually bring substance to the table because I have a technical aptitude and can bridge the gap between the application of the technology and the technology itself. So I'm able to kind of bridge that gap more of as a sales engineer than a salesman. So AE Building Systems really was designed to help builders, architects, homeowners, building owners achieve extraordinary energy efficiency objectives. And we went out and found different manufacturers that we could represent that actually helped to fulfill that objective. And that's where we've been since 2011. So this presentation will focus on why high-performance windows are important, what components within a window assembly help to make it higher performance, some of the benefits of energy-efficient windows and doors, but specifically how thermal performance impacts comfort, and as a result, energy efficiency. It's like one of the things that we struggled with is what's our message? And it's really comfort. You know, we're helping make comfortable homes. Oh, and by the way, we're also helping making them energy efficient. But anyway, there are also some really key attributes to how you install the windows that help make it perform better as well, the entire wall assembly. So I'll get into that a little bit. This last quote, it's the windows stupid. Sam Rashkin was the chief architect for the DOE buildings group, and he actually used that statement in one of his presentations about 7 years ago. It's the windows stupid. It's the weak link in our walls. So I mentioned Passive House, and I'm going to go into the design or the principles of Passive House just briefly because it is different than passive SOAR design. Passive SOAR design is largely mass and glass. You want as much glass on the south side as you can, then you want mass behind it to actually absorb all that sun that's coming in during the day, and then it'll dissipate into the house throughout the night and to keep the house relatively warm. Passive SOAR design is a little bit different. It incorporates some of the concepts of passive solar, but it's about optimization more than it is about mass and glass. And the design is important. Keeping the design simple, fewer corners, for example, shoebox is one of the concepts. You can have turns in your envelope, but ideally it's more of a simplistic design with fewer turns in the envelope. Turns in the envelope with a purpose is one thing I heard from an architect that does passive house design. Minimal thermal bridging. It's almost impossible to eliminate thermal bridging in a house. So it's really accounting for the thermal bridges and knowing where they are and making sure that you minimize them as much as possible. Air tightness is one of the most critical components of passive house, and it's 0.6 ACH50. Our code 2021 code, 2018 was the first time the U.S. had, or the IBC had a requirement on air infiltration, and it's 3.0. Passive house is 5 times tighter at 0.6 ACH50. ACH, is everybody? No, I better explain what ACH. It's air changes per hour at 50 pascals. So they measure the volume in the house, how much air is in the house, and then they blow it in or they suck it out. They determine how much air is actually going out that blower or coming in that blower, and then they figure out how many times the entire volume of the house changes in 1 hour. So 0.6 is less than one change, and I think that's to replicate, is it a 50 mile an hour wind? 24 mile an hour wind. It's 50 pascals. Thank you. I'm glad you're here. So a wind of about 24 miles per hour. So it's got to be super airtight, almost fishbowl airtight. Super insulated, typically there's double stud walls, or there's a stud wall with a huge amount of insulation on the exterior in the form of a Larson truss, which is a whole nother presentation. But super insulated walls. When we say optimized glazing, it's about, again, glazing with a purpose. It's not about having tons of glass on your south side, because you'll overheat in the winter. And John will testify to that previously, before you change your windows out. But even in the wintertime, you can overheat if you have tons of glass. And what happens with passive SOAR design houses, they'll get really hot in the daytime, and then at night, because the glass typically in the 70s wasn't very good, the temperature would drop at night. So you would have these big daily swings in temperature. Passive house is about making those swings extremely small and making it comfortable throughout the day. So it's about optimization. And then finally, because it's so airtight, you have to have mechanical ventilation in a passive house. You have to bring fresh air in. The key is you use an energy recovery ventilation system to reduce the energy losses. So when you got fresh air coming in through your walls because they're leaky, you have cold air coming in the winter, and you have hot air coming in the summertime. And with a passive house, you don't want that. You can't have that. But you can bring fresh air in and then exchange the heat of the air coming out and put it into that incoming airstream. So you're basically doing an energy recovery process. So those are the key things with passive house. And I bring this up because that's kind of how I got into this, but also windows are one of the most important aspects of passive house. I don't need to talk about it. So we're going to get into heat transfer when it comes to the windows in a lot of different ways. But anybody on the 3 forms of heat transfer? John, I know you know them. Go ahead, fire them off. Conduction, radiation, convection. So conduction is heat moving through materials, solid materials. Convection is heat moving through air, and then radiation is like my body's radiating heat right now, and the sun radiates heat. So I'm radiating heat, so heat goes to cold. So it's coming off my body and making the ambient air around me warmer. And my body's really warm right now because I'm doing a presentation and my heart rate's going. So, oops, and there they are. Sorry, I had it in the next slide. So, radiation, anyway, we'll get into those. Windows of the Week link, Sam Rashkin. So I wanted to give some background. These are some U values and R values of my house before and after changing the windows. And it's a measure of U values and R values when you're looking at just the window, just the wall, and the window and wall together collectively. So this first column, and I can't point to it, where it says walls and then R value 12, that's pretty much my house before I did anything. And then it says windows and doors, R value 2. That's before I changed the windows. So the the way that you get an overall R value for the entire house is as a weighted average of the two areas. So when you look at the walls and the windows and the percentage of the area, the total R value of my walls and windows together collectively is about 7. That was before we placed the windows. We replaced the windows in 2014-ish, and we put in R7 windows. And our walls are still R12, and our windows are now R7, but our collective R value went up 56% because we put in really good windows. Now, if we were to increase the R value in our walls by 5, like we did in our windows, we would only have gotten a 17% increase in the overall R value of the overall wall assembly, window and wall together. Does that make sense to everybody?
No, because the walls have a whole lot more area, and if you increase it by the same amount, you would expect a big improvement.
There's a law of diminishing returns with R value. So as the R value increases, the efficacy of the R value, we should do it this way, decreases. So it increases at a decreasing rate. So if you add from R0 to R1, you go up significantly in efficacy. But when you're going from R40 to R41, you get a tiny bit of increase in efficacy. So there's a law of diminishing returns, and here I'm doing it this way, but this is doing it the opposite way. There's a law of diminishing returns when you're increasing the R value as it gets larger and larger and larger. So when you're taking an R2 window and going to an R7 window, the impact is significantly greater than going from R12 to R17 in my walls.
Because it's down at the lower. Yeah.
Correct. Is that clear with everybody? Great. So this is another example, but in order to get my almost 11%, I'd have to bring my walls up to R42 with R2 windows, because those windows are such a sieve in heat loss. It's like a thermal faucet, essentially. I know that's hard to believe.
And those R2 windows would be double pane?
Yeah, it was old school double pane windows that we had in our window, on our walls. So that's the really important part of how windows impact the overall wall performance. So the components of the windows that are important, we have frames and different frame materials. We have the frame, and then we have seals, and better to show this one. When I'm talking about seals, this is an operable window. It opens, and we have different seals. So those are the seals that actually keep air from going between the frame and an operable sash, like a casement. And then we have the glass itself, the IGU. And within the IGU, we have gas or air in the pockets here. And then we have spacers. Pardon? Oh, my apologies. Insulated glazing unit. So this is the insulated glazing unit. So of a window, this is the IGU. And then the spacer is extremely important because it's the thermal bridge within the glass. If you're using aluminum in that spacer, and I'll get into this more later, it's a great thermal bridge because aluminum is a tremendous conductor. All right, so with the frames, we want the frames to be insulated. A lot of companies don't put insulation where those circles are. Those pockets will be empty. Like that pocket's empty, that pocket's, I got insulation here, but I can take it out, maybe not. But sometimes there's no insulation in these holes. And you can see in a fixed unit here, this entire frame is insulated. So it's really important that we have insulation. You can see the one on the upper right, that's an operable in this product. So it's a casement, and you can see that there's less insulation in it. So that frame is going to perform not as well as the fixed unit. We're going to get into that in a little bit as well. This next one is this window on the right side. And you can see it's a really thick frame. It's about 120 millimeters over 4 inches. But we have insulation here. We have insulation here. We haven't even have the spacers insulated right at the edge here. There should be, oh, there's insulation actually in the exterior frame as well. So everything's, not everything, but there's a lot of insulation in this assembly. And that's extremely important. This actual window is an R10 frame, which is unheard of in American window companies. This is actually a European design, but it's made in Colby, Kansas. Frame performance. So typical windows made in the United States might have an R value of maybe R2 to R4. A high performance window should be anywhere from R4 to R10, really. In R4 would be inoperable. It'd be your worst high performance window. Your fixed units typically are in the R6 to R8 range. And then, like I said, this particular window is R10. It's an R10 frame, just the frame. Okay, so different materials. Because this is wood, wood's only about R1 per inch, but because we have all these different insulation points where we're creating thermal breaks, that's what creates the R10 frame. But if we just looked at it from, if this entire thing were wood, it'd only be about R4.5, R5 if we didn't have the insulation in it. And then, oh, it was important to show you this one. There's a lot of aluminum windows out there that are all aluminum. But if they don't have a thermal break in them, you can see this area from here to here it's PVC rather than aluminum. If that weren't there, this would be a terrible window. You'd have ice on the inside all the time. If you didn't have that thermal break through the center there, it would be iced all over the inside all winter long. Whenever it's below freezing, it would be iced up because aluminum is a tremendous conductor. So aluminum is a terrible material for windows unless it's thermally broken. Then it can be great. All right, and then these are PVC frames, insulated. This typically is insulated. There's more insulation in this one. These travel and they get beat up. And then this is a fiberglass frame that's fully insulated. So it's largely thermally broken. We have one thermal bridge through here. So the different frame materials. Oh, we were going the wrong way. No. There we go. The other thing is air infiltration. So fixed windows have very low air infiltration, but operable windows can have a lot of air infiltration. So like sliding windows, they have a weather stripping around that operable portion. So you have a fixed unit here, you have a sliding unit here. That weather stripping around the outside really doesn't work that well. So casements and tilt turns typically have multiple locking points around the outside. So tilt turns are a European phenomena that's coming to the United States fast and furious. With a tilt turn, when you turn the handle and turn it inward, you go up to 180 degrees and it tilts inward. But then when you lock it all the way down, there's these pins all the way around the window that go into keepers and pull that operable portion of the frame called the sash to the frame. And it locks it tight to the frame. And there's seals that help to keep that air from going in and around. Where with a sliding window, that weather stripping typically is like a furry weather stripping, and it's not an air seal at all. It'll allow air through it. There's some better weather stripping and some worse, but we'll get into that a little bit more. And why is air infiltration important? So there's a governing body for the window industry called the NFRC. NFRC stands for National Fenestration Rating Council. And they have a number that's a threshold. So your windows can't be over a 0.3, and I'll explain this, but 0.3 CFM, cubic feet per minute, per square foot. So CFM, cubic feet per minute, a typical cubic foot not a typical, every cubic foot is 3.8 basketballs, approximately 3.8 basketballs. So if we turn this into a visual, 0.3 CFM for a 10 square foot window. So that's 2.5 feet by 4 feet, just typical size window, would be approximately 11.4 basketballs per minute at an airspeed of 25 miles per hour. So multiply by 60 minutes, 1 hour. You got 684 basketballs coming into one window. That's 10 square feet in 1 hour. Now multiply that by 30 windows, typical home. And you've got 342 basketballs per minute and over 20,000 basketballs per hour. So a good window should be 0.1 CFM per square feet. And that would be about 22 basketballs, which still sounds like a lot, but only 684 basketballs per hour at 30 windows in 1 hour instead of 20,000. So if we're using what the NFRC allows for, 0.3, you got really leaky windows, and you don't want that. The NFRC doesn't do us any favor by making that high of a threshold for people to meet, for manufacturers to meet. So it literally is a 30x difference. If a manufacturer just meets the minimum threshold or goes really big in high performance or airtight, it's a 30x delta. And typical casements, typical tilt turns, sliders will be real close to that 0.3 or that 20,000 basketballs for a 10 square or 10 square feet windows. A typical slider or a hung window, a single hung or a double hung, they're up in the 0.2 plus range, where a casement will be in the 0.01 range, and a fixed will be less than 0.01. It'll equal or be better than. So the air infiltration is huge when you think about it in the basketballs. You can get a visual for what that really means. And this is what I just mentioned. So the fixed windows are the best. And when we're talking to clients about windows, we typically would say, if you're never going to open this window, or if they're retrofitting an existing house and they're putting in another casement because there was a casement there, but they've never opened that window in their entire lives, we're saying, put in a fixed window because it's going to be more tight and it's going to be more thermally, it's going to perform better thermally as well. And then if they're wanting hungs, I always try a hung window, like a single hung and double hung. I try to get my clients to use casements because when you lock them down, they're airtight. They're 0.01 essentially versus maybe a 0.24, which would, our hungs are probably a 0.07. They're better, but they're still worse, 7 times worse than a casement. So we do try to get them to change their mindset about that, what type of window they should be using. So typical windows that are in a lot of homes and a lot of manufacturers are still making just your basic double pane windows. The manufacturers that we're working with are going up to quad, and they're using krypton gas in them. So this is the one on the far right. You can see there's 3 spacers, 4 panes of glass, and they'll use krypton gas and they'll get extraordinary performance out of that window. But then we have the law of diminishing returns. And once we get up that high. So the key is it isn't just having multiple panes of glass, because you can get extraordinary performance out of just a triple pane, not having to go to quad pane, by having a bigger or deeper IGU. So this is a 1 5/8 inch IGU. The Europeans are using 2-inch IGUs. So they're 2 inches wide. IGU, insulated glazing unit. That's this thing. It's just the glass part of the window. Yeah. So they'll have another, 5/8, 3/8 of an inch wider IGU, deeper IGU, and they'll fill that with argon. And
what's the gap that they're filling? Yeah, not the total, but you've got the glass or the divider in the middle. So what's the...
This has suspended film in it instead of glass.
Fine. How big is this?
Got it.
For those good windows that you're talking about.
So it's 2 inches wide. You have 4mm glass. So that's quarter inch. So you're quarter inch, 3/4. It's not quarter inch. It's 1/8 inch. So 3/8. 2 inches minus 3. 1 5/8 divided by 2 is 7 9/16. Is that right, Craig? So over 1/2 inch be in each gap. No, it'd be more than 9/16. 1 5/8. 3/4. You're right. 3/4 of an inch in this hole. Where this is, is less than a half. It's right around 1/2 inch in this gap. So, but you can see this window will not fit in this opening. So they're using, this is a European frame, and it will have a 2-inch IGU, 2 inches deep IGU with argon. And they're getting literally 0.1 U value and R10 out of the glass, center of glass, when they're 2 inches. Now, Alpine, does the quad pane. We don't have a quad pane with us. They're putting krypton gas, and it's only 1 5/8, and they're putting krypton gas, and it's 4 panes instead of 2. And they're getting down into a 0.06, which is about an R16 at the center of glass with krypton gas. And we'll talk about krypton in just a minute. I have. And actually, Alpine has experimented with it a little bit. And I'm not super familiar with results, but I've heard into the tens of R values, and I don't know how much. I'm waiting to hear when that actually becomes commercially viable, because right now it's still not commercially viable. Is that right? So R21 in vacuum insulated? Okay. Yeah. Yeah. So Alpine's been experimenting with it. Alpine pretty much leads the charge in the United States as far as like new stuff, experimenting with various things. One of the things that they led the charge on is thin glass. You can see the middle pane is super thin. Thin glass, Alpine put it into commercial use 3 years ago. Well, I guess they did their first experiment about 3 years ago, 4 years ago, and then they went into production maybe 2 years ago. But, thin glass started... It historically was very expensive to make because it's so skinny. And they learned how to make these huge sheets of thin glass. And in the end, Alpine did some experiments where they put it into a storefront and just test it, see how it performed. And they eventually went into production about 2 years ago. Yeah. So when it comes to performance, gas matters. Most manufacturers in the U.S. will say in Colorado, well, you can't do gas, you're at elevation. And that's wrong. It's patently false. There's 3 different ways to actually do gas at elevation, and I'll explain that in a minute. But argon, just to talk about the 2 different gases that are typically used in windows, there's xenon too, we won't go into that very much. But argon's cheaper than the bottle it comes in. It's actually pulled from the atmosphere, where krypton's mined, and it's a lot more expensive. It's more dense and it performs better, but it's also a lot more expensive. So it is the density that reduces the conductivity of energy through the window, so the density of the gas. Most manufacturers say that you can't do it at elevation because when you seal a window properly around the outside, so the glass itself, this is the seal on the IGU, goes around the entire outside. When you seal it properly and it's fully sealed, and you take this up to Leadville, it'll blow up because it's sealed and, it's the bag of potato chips. The glass will actually blow. It'll break. And I've seen it where it's exploded. Sometimes it'll pop and the air will escape, but I've also seen it where it's literally exploded. So in order for that gas to stay in and not blow up, there's 3 different ways to manage that. The Europeans are using, it's a pressure release valve, so once the pressure hits a certain threshold, the gas will actually escape, or the air will escape. you typically fill the IGU about 90%. At NFRC, it has to be at 90% or higher. Alpine shoots for 95%, so the very top is air. And you typically would put the valve at the top. So if anything does escape or come in, because it's a pressure release valve two-way, it'll be air that goes out and comes in, because it's not that much that's going to be leaving or coming in. Alpine uses a balloon system. It's actually like a lung. So there's a breather tube that comes out of the IGU and out of the frame. So you would see this breather tube at the top that comes out up here, and then there's a balloon attached to that. That balloon that allows, when you're in the Eisenhower Tunnel, for example, the balloon will be full. But when you're in Denver, before you leave, it's empty. And then when you get back into Silverthorne, if you're going up over, it'll be empty again. It actually will breathe like a lung, essentially, and it allows that pressure to escape. Another way is, and there's a company called Zola that does this, but they pre-pressurize in the factory. So if it's, and those are made in Poland, but if you're going up 10,000 feet in elevation, they'll pressurize it for 10,000 feet when they're at sea level, essentially, which is a little frightening. It might implode. But that's another way to manage barometric pressure changes. So the manufacturers are correct that it's hard to do. It's really not that hard to do, but it can be done. They're incorrect about that. It can be done, gas at different altitudes. So don't let anybody tell you that you can't do gas at elevation. One thing that they will say is that, well, it leaks anyway. And yes, it does. About 1% a year. So in 50 years, you still have 50%. Well, if you fill to 95, it's 50%. So what does that mean as far as performance? A double pane window, center of glass, is about an R3 to R4, 4.5. And that's at the middle of the glass. And I mentioned center of glass because it's probably a better measure when you're looking at just the IGU itself. Because the frame, it can be made from anything. If you have just really crappy aluminum frames that aren't thermally broken, there's basically no R value in that. So I'm really talking about the center of the glass. Triple pane glass, depending on the coatings, because with triple pane, with double pane as well, there will be coatings on the inside of these two panes of glass. These coatings, there's a ton of different types of coatings that achieve different objectives. So if, for example, you want really high gain, there'll be a different type of coating that allows more radiation, solar radiation, through the window. If you are, let's say it's a window on the west side and you want to prevent overheating, they'll put low solar heat gain coatings on the inside of this window. The key is the coatings also impact the thermal performance of the U value. They don't just impact how much solar gain's coming through, they impact how well it performs thermally. So that's why I have the big range, R6 to R9, on just triple pane. Hopefully that makes sense to everybody. Let's see. We already talked about that. Good. What do you want?
So I worked with Alpine on what is center of glass definition, and it happens at about 3 inches from the edge.
Yeah. Yep. It's not just in the very middle. It's got to be far enough away from the spacer, essentially, because the spacer is that thermal bridge. Okay. So when I mentioned these coatings, we got high gains, low gain, and I mentioned you might want a low gain on the west side. In the front range, because the way the sun comes over a house or a building in the summer, you get cooked in the morning. You got to do it backwards. You get cooked in the morning and you get cooked in the afternoon. So the sun comes over, and by evening, you're really getting baked because the house is already warm. Now, in the winter months, that sun actually comes around the south side. So we want that winter sun in order to heat the house. So we'll use a high solar gain glass on the south side. On the east and west, we'll use low gain to prevent overheating and reduce that high, delta in temperature throughout the day within your house. So this is the information. We call it tuning the glass. And, this is what I wanted. So in the Front Range, we almost always use low gain on the east and west. And then that's called solar control. On the south, we always use high gain. And then on the north, it varies. It's kind of a personal preference. We generally want the best U value on the north, but the delta between high gain and low gain in U value or thermal performance isn't that big. So some people want more natural light. And there's another measure. You got U value, you got solar heat gain coefficient, and VT. VT is visible transmittance, and it's a measure of natural light. And typically, the higher the gain, the more natural light. So we'll use high gain on the north side sometimes if they want more natural light in their home. And that's more of a personal preference. The middle gain actually gets the best U value for Alpin. So some people will put the best U value or the middle gain on the north side because you don't get any heat over there, and you want to reduce that heat losses. In the mountains, a little bit different. Because like Leadville, they have heating loads even in the July. It's 45 degrees in the morning. So that morning sun's a bonus. So using a high gain on the east side is actually a bonus up in the mountain towns. So we might use the middle or the high gain on the east side, because they won't have as much overheating in the morning or the early part of the day. I'm gonna do this. Oh, we already did that. That's talking about balloons, valves, and pre-pressurizing in the factory. Spacers are critical. So it is the thermal bridge in the window, and there are a lot of different materials that you can use for the spacers. So the spacers, the material that goes in between the pieces of glass. So this is a film here instead of a piece of glass, but that portion right there, the silver part, is the spacer in this one. So if we're using a metal, it's going to be a better thermal bridge. Now, there are different metals have different U values or different conductivity. Aluminum, for example, has tremendous conductivity. We used to use it for electrical wires. Galvanized steel has tremendous conductivity. Most U.S. manufacturers are using those two materials because they're cheap. Alpin uses stainless steel because it's a terrible conductor. You'll notice on stainless steel pots and pans, there's copper on the bottom, and it's because stainless steel is a terrible conductor. So as far as metals go, if you're going to use a metal, use stainless steel. Now, this is a European window, and you can't really see it, but it's a composite, a composite spacer. It's not made of metal. It's made of a plastic composite, and I can't remember. I'm drawing a blank on the name of it. But the material in there that you see, it's kind of brown. I don't know if you can see that. That's a desiccant. It's not actually insulation, but the material on the spacer is a composite, and this is an example of what the Europeans are using, and I'll just send it around if you want to. Now, Alpin, having gone to thin glass, has changed their spacer to a high-density foam spacer. And this is the type of spacer that they're using in Colby, Kansas as well. But Alpin's using a high-density foam spacer that's a thermal break, and it actually improved the performance of the glass, just the IGU, the entire overall assembly by about 18%. Just changing the spacer from stainless steel to a high-density foam.
And this foam is what kind of foam?
It's a real high-density foam. The key is the thermal bridging in this. I don't know how to explain because I'm not great at thermodynamics.
My question comes down to durability.
Yes.
Because what kind of foam goes in there is going to break down in the sun or not.
It's actually protected by the coatings to some degree, UV protection. So it's I mentioned the coatings that are on the inside and the outside of the inside portion. So that protects that foam from any UV exposure, not any. It'll get UV exposure. I'm going to have to get back to you on that because I'm pretty sure there's UV. They wouldn't be putting them in windows if they hadn't already thought about the UV exposure. But yes, point taken. And I'm going to give you a piece of paper and write your name down and your phone number and get back to me on that. Bruce, do you have? Yeah. So it's a great question. I haven't asked the question myself, so I don't know the answer to it, but I'm sure that they've thought of that. Yes, there is a foil on the outside of it, but yes. This is a thermal image of a window showing the importance of the spacer. So all of that red up there is actually heat flowing through the window via the spacer. So this is probably an aluminum spacer that's conducting tremendous amounts of heat out of your house in the middle of the winter all the time. And that may explain why it's such an impact. You can see how that's lighting up. Spacers also contribute to condensation. So when you have condensation on your windows, it's almost always around the outside, right? And where do you have ice? Around the outside. If ice starts to build, it usually builds around the outside, near the spacer. And it's because all that heat is going out through the spacer, and as a result, it's crazy cold right there at the spacer when it's, say, 0 degrees outside. So because of the condensation, you end up with, mold and rot if you have wood windows. Wood being a food source for mold. But also you can have mold on fiberglass and you can have mold on PVC, for example, because dust will collect on the edge of the windows. And then you've got the moisture and the food source, dust being the food source. You'll have even mold on fiberglass, which we don't want. Pardon?
Mold
on aluminum, exactly, because there's a food source, it's dust or dirt of some sort. I already mentioned this. Going from it was a different one, but going from a galvanized spacer to a stainless steel spacer improved the performance of the window overall, not just the spacer section, but the entire window by over 13%. So it really makes a tremendous difference. And then we went from stainless steel to the high density foam super spacer that they're using. It was another 18% improvement in the overall window performance. So the spacer makes a huge difference. Okay, so components, we just did all of those. Okay, ramifications. One of the things that people think they have in their homes is drafts when the wind's not blowing. And cold, what will happen in a house when it's super cold outside, warm inside, is that surface temperature on the inside, if you've only got 2x4 walls like I do, that inside surface temperature gets cold, the air next to it then also gets cold, and the air drops. Colder air is heavier than warm air. The warm air then will fill that space. That cold air will pool, and eventually you get a convection current. When that happens, people think, oh, we got drafts in our house. And we really don't. What you have is a microclimate in your house. Because the wind's not blowing, you don't have a draft. What you have is air just literally doing this circular motion because you've got this cold surface. So a bad window, literally on a 20-degree day, might be 45-degree surface temperature on the inside. where a decent triple pane might be 62 on the inside. So you don't get that draft. And the important part of that is it's a 7.2 degree delta. So 7.2 degree Fahrenheit delta is enough that convection starts to happen in your living room, literally, or your bedroom. So if you have a 7.5 degree delta between the ambient air and the inside temperature of a surface, then you start getting that convection current. And this explains it a little bit more. Let's see. Yeah, and it's critical. That's actually part of the requirement at 7.2 in a passive house window. And they call it a hygiene metric, and I don't know why they call it hygiene, but they call it hygiene. Welcome. So, all right. So one of the, I was going to say unintended consequences, unintended benefits of having high performance windows is they're quiet. Because one, they're airtight, so sound travels through air. But also with multiple panes of glass, you just have much higher STC ratings. STC is sound transmission classification. And from my understanding, it's a logarithmic, so it increases at an increasing rate. So for every one, it increases at an increasing rate, you get more efficacy out of the next number. So when you're going from, say, a 20 to a 21, it's much better than going from 0 to 1. So it's the opposite direction with STC ratings. So a 2 by, what is STC? So a 30 STC is what you're typically going to get with a high performance window. It can go up higher significantly. So for example, if you're using dissimilar size or thicknesses of glass, i.e. we have a thick piece of glass, a thin piece of glass, a thick piece of glass, the different thicknesses actually eliminate different frequencies of sound. So that's another reason why your STC rating might be better. So it's an unintended benefit of having high performance windows is having very quiet house. And also with passive houses, they're so quiet that, it's people, it's almost a Zen feeling because they're just super quiet homes. We've had people complain a little bit about their ERVs, ventilation systems in a passive house, because they can hear the motors running. But in a normal house, it's like a furnace that comes on and it blasts the whole house and there's tremendous amounts of noise. You would get completely blasted out if you're in a passive house because they're just so quiet. And the windows are part of that. So to include the air tightness as part of the reason. When we get into installation of windows, there are a number of considerations. The Germans pay about, I don't know, 5 years ago, it was like a 3.5x for a kilowatt hour. So they're splitting hairs because every kilowatt hour they pay for makes a difference. So they're paying at least 3 times what we're paying. And since Ukraine, I think it's probably 6. So they're paying a lot more for a therm, and they're paying a lot more for a kilowatt hour. And they've modeled where do you put a window inside a wall assembly. So they're making really thick walls. Instead of a 2x4, they're doing like a 12-inch wall. And they said, okay, well, what if I put it on the inside, closer to the inside interior of the house, or to the exterior of the wall assembly, or to the middle of the wall assembly? And they modeled it in thermodynamics and determined that in the middle of the insulation layer is where you want to actually install the window. And then that helps the entire wall perform better. And this is where I'm a little bit outside, well, I'm a whole lot outside of my realm of expertise because I don't have a big background in thermodynamics. But the energy modeling that they did, they said that middle of the wall is where you want it. Now that presents problems or challenges because when you put the window at the middle instead of to the exterior, now you got to figure out how to make water drain out of that space and make sure that it doesn't get into your wall assembly below the window. So there's a lot of considerations related to that as well. So let's see. And then there's also preparing the window before putting the window in. So this area up here, right at the front of the wall assembly, there's sheathing. And if you don't put the tape over the gap between the sheeting and the framing, you'll have air infiltration right there at the sheathing to framing connection. So preparing the window opening means also making sure that everything's airtight before you put the window in, and then again after you put the window in. So you want to tape the window at the head and the legs after it goes in, and then on the inside, you put tape around the entire inside perimeter of the window to the frame to make sure that it doesn't leak air on the frame to framing, the window frame to framing gap, because there's usually about a 1/4 inch to a 1/2 inch gap between the window and your wall framing.
Do the windows get buttered in with caulk as well?
A lot of folks do. So if they're doing a window, this is where they're installing it onto the exterior of the wall assembly, and they will tape, or they'll caulk this gap here between the nail fin and the wall. So they'll put caulk on that, and then they'll tape the outside of the nail fin as well. So that's a different type of install, or that's actually a more common type of install for the United States. That's why there's a rough opening gap between the framing, the actual framing. It's so that the wood in the wall will be able to move, because it'll move with heat and moisture, and you'll have different expansion coefficients. So you want a 1/4 to a 1/2 inch gap between your window and the actual framing. And that's where you need flexible caulk, or actually flexible tape, to make sure that it actually move with the different materials appropriately.
And have these tapes been tested for durability of the adhesive and of the material itself?
Yes. So what most builders have been using in the United States is a petrochemical-based adhesive, and that's not a good thing, because as soon as you open it, you can smell it, and that means it's off-gassing from the moment you open it. The European manufacturers and builders have been using it's an acrylic adhesive that doesn't smell, and you can get a little bit of an Elmer's glue, but they say for the life of the building. This is a product made in Switzerland, and when they do a presentation, they say for the life of the building. In Europe, the life of the building is much different than the life of the building here in the United States.
People with chemical sensitivities are going to want to know about this paper.
Yeah.
Yeah.
They love knowing about it. I know. There are good products out there, acrylic-based actually as well. I'm not super familiar with them, because I think that they're more labor-intensive. I'm very familiar with this product. I feel like it's an expensive product, but it's also less labor-intensive than the liquid flashing. You typically have to trowel that liquid flashing on, and it takes a long time. So it's asking the builder and his crew to do a lot more. These tapes go on pretty easily. You can roll them out, and they're adhered. And the adhesive actually grows over time. The adhesion grows over time. You don't want to stick that to something you don't want it stuck to. Seriously. Yeah. So we talked about that drainage plane. This is one way to manage the drainage plane at the base when you've got a really wide assembly and you're putting the window in the middle. This sill at the bottom here is a European phenomena, but it's called a Gutmann sill, and it will bridge the gap from the window all the way out to the face of the wall. There are other options, like it's this guy right here and up there. This one goes all the way around, but it actually will bridge the gap from the frame of the window to the exterior as well. Alpine actually provides this one. And that's, yeah, it's a close-up of it. The left side here is that extension, so you're able to put the window more closer to the middle of the window.
And are these compatible with all kinds of siding?
Yeah, you'd bring the siding right up to it and then caulk the joint. So yes. In fact, this particular detail is really made for a continuous insulation layer on your exterior wall. So this would be insulation. There's your framing. And then you're bringing your finished material, your exterior finished material up to the window there. Does that make sense?
Is it compatible with earthen material?
Yeah. You can bring like a stucco or that's sort of an earthen material, but you could bring a stucco up to there. There are some considerations that you want to work through with your builder, but yes, most certainly. And sorry, Bruce, I know we weren't supposed to have questions. I prefer the interactive. It's all good. People forget their questions. Oh, for certain. Okay, thank you. So one of the reasons, I mentioned getting into this because we had kids and I needed to stop traveling, but I also realized when we had kids, it's like, oh, we're really setting them up for a mess in the future, their energy and their environmental future. So it really is the right thing to do, is to build higher performance, to retrofit higher performance and make buildings perform better in the long run, so we're not using so many petrochemical products and just burning through these fuel sources that our future generations might actually need. So it's a combination of doing something that hopefully will make a difference in the future, but it's also, who doesn't want a comfortable house? We've got one room in our house that we have to wear blankets on. It's our TV room even. And we're covered in blankets because it's the worst room in our house and it's crazy cold. And when you build a high performance house, you don't have those cold spots. You have a comfortable house and it's comfortable throughout the day. It doesn't swing. So, it's like one of our clients one time, they had a breakfast buffet, a breakfast nook, and it was it's just surrounded in glass. And they couldn't even use it in the winter. They wouldn't even go into that space. But when they replaced the windows and made some improvements to the exterior, they were actually using it every day in the winter. It's to some degree a game changer. We made a lot of changes to our daughter's rooms because they were just cold. Of the 6 sides of their cube was a floor that was over a garage and 2 walls and a ceiling that had an attic above it. So they had 4 sides that were cold. And to make some changes to, one, the windows, but also the insulation around, it just changed the way their room lived. It was just more comfortable space to be in. So it really is about comfort. But it's also about mitigating risk. What if energy prices go up extraordinarily like they did last winter? Our heating bills went up a lot, but we still only paid $1,200 for the entire year. At Passive House, a fraction of that. So it is a risk mitigation effort. It's about energy independence. If you can go zero energy, for example, you're no longer reliant on Excel for energy. Let's see, building resilience. When you're building to Passive House standards, you're also building in a way that the home is truly going to last longer. It's more scientific approach to building a house, making sure that your walls aren't going to fail. So there's a resilience component of it. And then, of course, you can go off grid much easier. But there's a lot of reasons why to do high performance windows, but high performance construction in general. All right. I think that's the end of it. This is reviewing questions, and I don't think we need to review, but questions? Further questions, right. I'll go left to right, my left to right. Go ahead.
So just curious, you mentioned passive house. Other than windows, if you have like a single family home from the 70s or 80s, is it possible to convert that or get that to passive house levels or start to approach that?
There is a
would you do?
retrofit standard. That's a passive house retrofit standard. It's not as rigorous because it's almost impossible. And the reason I say that is typical homes built, like mine's in 1971. For me to retrofit it to passive house standards would require me to remove the concrete in our family room. The floor is concrete. I mean, we'd have to insulate underneath. We'd also have to excavate outside and put insulation. It's a tremendous undertaking. It is possible, but it requires significant resources. But you can make tremendous improvements in an existing house. Like, for example, I said $1,200 last year, but in 2017, I think our whole bill for the entire year, we do have solar on the roof, is like under $400. So you can make extraordinary improvements to an existing home. And yeah, John will.
Well, Bruce and I have super insulated our houses. If you want to see examples. So Bruce and I have both super insulated ours from early 80s. This is my brochure. I'm open 7 days a week. This is a Jimmy Carter NREL project house that I helped to build in 1981 as my forever house. It's got the top of the line Krypton Alpine windows, which was a huge difference. But there's so many things to consider. Combination of this is a passive solar heated house from the 70s versus passive house. And now I have passive house certified thick walls and windows, which totally was a game changer.
And I also did a deep energy retrofit on my house. Mine's a circa 1996 tract house. So we covered the outside of the house with 4.5 inches of polyiso foam, replaced all the windows with top end Alpine. So Todd mentioned ACH 50 values of 0.6 for passive house. My house is 0.68. So it's pretty darn good.
For retrofit, the actual number is 0.9, so he's exceeded it. Yeah. Okay. Yeah. And just go across.
We got Alpine sliders, triple pane fiberglass framing. How much better are they than the conventional sliders? And how long would the seals last before they need replacement?
And this is sliding door.
No, sliding window.
Sliding window. So a typical, like air infiltration for Alpine, I think is 0.07, where the casements are 0.01. A typical American window for air infiltration is probably going to be around 0.225 instead of a 0.07 or 0.01. It's a lot worse as far as air infiltration. How long will the seals last as far as the seal around the glass or the seal? You might need to replace that weather stripping at some point, but I doubt it anytime soon. Yeah, probably 15-ish. I don't know to answer that. And just give them a call. They'll send you some. Yeah. Don't tell them I said that.
Todd, with the anniversary of the Marshall Fire approaching, one thing that I wonder about is how do the high-performance windows and doors perform in regards to fire resistance?
Yeah, and that's really a material discussion, but one of the keys is if you've got a single pane window and enough heat, it'll break and shatter and you're burning quickly. Double pane, actually wildfire requirements in California say either 2 panes or you use tempered glass. So you don't have to have tempered glass. So 2 panes is better than 1 when it comes to fire, and then 3, of course, is better than 2. Tempered glass is even better than if you're using tempered glass, then you're even exceeding more because tempered glass is already heat treated and it's not going to break with too much heat. Then when we get into the materials, generally, I think wood is actually okay. It's not good, but wood clad is good because you're going to have that aluminum cladding on the exterior to help protect the wood from burning. Aluminum is going to be a tremendous product in the case of a wildfire, just because it's not going to burn at all. Might melt after 2,000 degrees. I don't know what the melting point for aluminum is, but so it's the frame material then becomes a little bit more relevant. Fiberglass melts in like a fiberglass window. This one here, fiberglass. I think it's around 1,300 degrees. Glass melts. So fires will go up to 2,000. So eventually, it's gonna bad wildfire is gonna melt it eventually. I've heard of wildfires going up to 2,500 degrees. Which is going to melt steel. It's going to melt. The steel will bend. I don't know if you saw, but there were some girders that were bent in that fire because it got so hot, the Marshall Fire.
A lot of the Marshall Fire rebuilds are using passive house window technology with multiple glazing, particularly for the fire resistance. And that's one of the prescriptions that you're trying to build a fireproof building. Good glazing is really important.
Yeah. Boulder actually has approved composite plastic or PVC. So you can use, when I mean by composite, it's reinforced with some type of material. This particular PVC is reinforced with fiberglass. Short fibers makes it stronger. So it's going to last longer and protect the house longer than a typical PVC would melt very quickly. Or start to warp and change shape very quickly. So the composite PVCs are actually approved by Boulder and I think the California wildfire, they don't actually put a requirement on the material of the frame, only on the glass because the glass will explode or shatter with enough heat.
Well, I think you just answered my question, but I have another one. We've got a 54 brick ranch, and we ended up doing triple pane wood pellets 15, 17 years ago because that was about the best we could do. But we're debating downstairs. We did vinyl double panes in the smaller windows. Would it be wise to replace those with something more efficient?
You said downstairs. Is this an area that you live?
Yeah, we live in the whole house. We do. Yeah, it's a brick walkout, and yeah.
Got
so
it. Okay. I was thinking maybe it was a basement.
well, it's a basement, but we use it. Yeah.
Understood. It's one of those things where it might even be worthwhile getting a laser thermometer and seeing what the inside temperature of those windows is this winter.
I will do that. Yeah, we've done blower tests and all that, but we haven't done that. So perfect. All right. Thank you.
Yeah, check them on a cold day, and if it's 45 degrees on the inside, then that's not a good thing. And they probably will be.
I think if your windows are more than about 10 to 15 years old, they're obsolete and need replacing. is my rule of thumb.
Right. Right. Any other questions?
What are delivery times on these high performance windows?
It depends what time of year it is. But also during COVID or right after COVID, when the supply chain, we went up to 20 weeks. We've got, and this guy is running a good 6 to 7 months. It's really the craftsmanship is tremendous, and they take forever to build. So, and he also gets his glass from Europe, so he is waiting for that. So this is a 6-month deal, but Alpen typically is running in the summertime 8 to 10 weeks, might go to 12. in the spring and fall. One of their product lines right now is running for 5 to 7 weeks. So it's pretty quick. That's a great question. So, well,
Repeat the question.
oh, where do you,
How and where do you source your
materials? So glass for Alpen is made here in Colorado. There's a glass floating plant, Cardinal plant up in, I think I want to say it's Longmont. It's off I-25. It's not far from there. Then the frames are sourced. They have 2 different product lines. This is actually a German frame that they bring over containers of long lineals that fill the entire container. So it does travel over the ocean. The spacers come from, I want to say, the Midwest, but I cannot remember. This is the fiberglass product, and again, the same glass. It's all Cardinal, and it's locally sourced. The frames are coming from a company called Inline near Toronto, so in Canada, but not quite as far away. The advantage, this is the SmartWind product. He tends to be very picky about his wood and won't get it from just anyone. He tries to get old growth from Canada. And it's hemlock typically is what he's using. And it's a tight pattern grain, but he's very particular about what kind of wood he uses because he wants it to be the best, dimensionally stable, etc. But his extrusions, the aluminum comes from Gutmann out of Germany. And they do have a U.S. presence, but it's probably made there. I think the wood fiber, unfortunately, the insulation is coming from Europe as well because we don't have a lot of manufacturers that do that. Yeah. Any other questions? Huh? Not too bad.